We're going to be talking about electrolytic cells and electrolysis. You might remember that we talked about the fact that there's two types of electrochemical cells. Galvanic cells is what we have been talking about so far, which is where you use a spontaneous chemical reaction to give you electricity that you can use to drive an electronic device. What we're going to be talking about now is an electrolytic cell in which we're going to force a non-spontaneous reaction to occur by utilizing a current, by actually driving it by applying electrical power to it. Now, a non-spontaneous reaction is one that has a cell potential that is negative and therefore one that has a positive delta G. All right, so what are the differences? Here I have a normal galvanic cell. This is what we have already been talking about, where at the anode we have the oxidation take place, where electrons are being released, and those electrons go from the anode toward the cathode. And then what else do we have? We have that at the anode we have the oxidation take place, at the cathode we have the reduction takes place, and so on and so forth. And notice that the electrons are freely flowing and they provide us a voltage. That voltage is our cell potential, right? Now, what we're going to have is the same case scenario, the same ions, the same zinc and zinc ions, and the same copper ions and copper, but now we're actually going to go and apply a external power to it. And so we're going to see what changes once this becomes an electrolytic cell. So in the electrolytic cell, we have a power source that drives the electrons to flow in the opposite direction, right? So we're going to have now the electrons coming this way. And so now the zinc, instead of being oxidized, now there's going to be a reduction taking place here. The reduction is that the zinc ions are going to combine with those electrons that are coming here and to form zinc plus. So notice that the opposite process is happening to what we had in the previous slide. Okay. At the same time, since we're forcing the electrons to leave from this side, we're forcing this other reaction to take place, where now the copper solid is actually becoming copper 2 plus and releasing 2 electrons so that those electrons can actually go in that direction. Now notice that since this side we have a reduction takes place, now this is going to be called the cathode, but the cathode is negatively charged now. That's something that is different. The right hand side we now have an oxidation takes place, so that's going to be our anode, but notice that now the sign is going to be positive. So we can already see some things that are different and some things that are similar. What's still true for both the galvanic cell and an electrolytic cell is that the reduction occurs at the cathode and the oxidation occurs at the anode. Now, what has changed is the sign. The sign of the anode is now positive. The sign of the cathode is now, let me zoom in the right place. The side of the anode is positive. The side of the cathode is now negative. So that has been different. Okay, we have gone over this and this. Now, the electron flow is different, right? The electron flow is going to be, is in the opposite direction, but it's still going from the anode toward the cathode. That's still valid. Another thing that is different is that we're utilizing a non-spontaneous reaction. We're making it happen in that way, right? We are going to have a cell potential that is less than 0, and therefore we're going to have a Gibbs free energy that is greater than 0. That's something to remember. And of course we have a power source. Those things are different. Now, one other thing that we haven't talked about is the salt bridge. In the salt bridge, the same thing that you predict is going to happen. Since in this equation we are losing positive charges over time, what we're going to have is that a positive ion, let's say sodium ions, are going to come from the salt bridge into toward the solution here. On the right hand side, we are generating more and more positive charges, so negative charges are going to have to come and balance that out. So let's say that here we're going to have a nitrate ion coming toward that direction. That's if my electrolyte here was sodium nitrate, then I would have sodium ions and nitrate ions going into those directions. So what's still true, still valid for both galvanic cells and electrolytic cells is that the cations end up going toward the cathode and the anions end up going to the anode. So this is a good summary for you guys to have to see what's different and what is the same. Now, we can actually utilize these electrolytic cells for at least two different things. One of the things is to produce metals through a chemical reaction. The other application of an electrolytic cell is to plate or electroplate metals, and that might be something that you might be familiar with in terms of electroplating, like silverware with silver to make it shiny again after it has been oxidized for a long time, or electroplating of jewelry. So let's look at this. These are the calculations that we're going to be doing. These calculations are going to enable us to calculate how much metal we can produce or how much mass of electroplating metal we are producing onto a material. The equations, they look complicated, but they're actually kind of simple. In this case, we're utilizing dimensional analysis, and I'm hoping that you guys are familiar with that. If you are not familiar with dimensional analysis, you can separate this into individual calculations, like one step at a time, but it's going to be more time consuming. All right, the calculations are as follows. Typically, you're going to be told that you are doing a reaction for a particular set of time, so a particular time, and a particular current is being applied. So your current is capital I, your time is T. The current is in amps, and an amp is equal to a coulomb per second, which means that your time needs to be in seconds. So the first three calculations here is taking the hours and converting to seconds. And you can do that separately if you want to. There's no problem with that. So basically you take the hours and you convert it to minutes by multiplying by 60 minutes. And then you multiply the minutes by 60 to convert it into seconds. Then you multiply the seconds against your current, which is in coulombs per second, in order to get the coulombs. The coulombs is basically the total charge that you are applying to that electrolytic cell. From there, we need to convert the charge into moles of electrons, and we do that by utilizing Faraday's constant. Notice that we are dividing by Faraday's constant, and the reason, well, I mean, the way that I know to divide it is because I need to take the coulombs and I need to cancel those coulombs. And since we have 96,485 coulombs per mole of electron, then I have to divide by Faraday's constant. Once we have this mole of electrons, then we need to figure out how many moles of electrons are going to convert into how many moles of a metal. And that's by looking at the equation of the reaction taking place. For example, if your equation had been copper 2+ being converted into copper solid, then we know that for every 2 moles of electron, we are making 1 mole of copper metal, right? Just by looking at the coefficients, a 2-to-1 ratio. And I know that I have to divide here because I'm starting with the mole of electrons on the top, so I have to divide by the moles of electrons, which is 2, and I have to multiply by the moles of the metal that I'm trying to make. And finally, once I have the moles of the metal, I can convert it into grams by using the molar mass from the periodic table. And I know that I have to multiply it to be able to cancel the moles away. Again, you can do this in several steps using either small dimensional analysis parts or by using cross multiplication. There's no problem with doing that. You're going to get the same answer as long as you're making sure that you're multiplying or dividing by the right thing. So again, the steps is that you're first going to find the charge by multiplying the current against the time in seconds. Then you're going to convert those coulombs into moles of electrons by using Faraday's constant. Next, we're going to convert the moles of electrons into moles of metal by using the coefficients of the balanced chemical equation. And finally, you're going to convert the moles of that metal into grams by utilizing the molar mass. I recommend that you guys look at the video, which is in figure 19.17 of the book, and look at practice problem 19.21. Now, we're going to do a problem right here. So the first one is an example of electrolysis to produce a metal. And the question is, what mass of cobalt metal can be produced from cobalt 2 plus in 1 hour with a current of 15 amps? All right, so, okay. What we need to do is to set up our equation. And so remember that the first thing that we're going to do is to take our current, which is 15 amps, and we're going to remember that 15 amps is the same thing as 15 coulombs per second. And so we said that the first thing that we were going to do was to multiply that current against the time, but the time has to be in seconds. 1 hour is the same thing as 60 minutes, and 60 minutes, each of those minutes have 60 seconds. So 60 times 60 is 3600. So I'm going to take my current and I'm going to multiply it, coulombs per second, and I'm going to multiply it by the seconds, which is 36, 30, nope, does not want to do 3, 3600 seconds. And I'm actually going to do this problem step by step as opposed to using dimensional analysis, just in case that you didn't like that other method. But it's basically the same exact thing. So now I'm going to get a number here, which is 54,000 coulombs. Okay. The second step was to convert those coulombs into moles of electrons. And to do that, I'm going to use Faraday's constant, right? So I'm going to take my 54,000 coulombs and I'm going to be dividing by Faraday's constant, where Faraday's constant is 96,485, and the units of that are coulombs per mole of electron. And so I'm going to get the moles of electrons on the top, and that's going to be 0.56 moles of electrons. The next step is to convert those moles of electrons into moles of the metal. And to do that, I need an equation. So here, I was not given an equation, but I was told that I'm using cobalt 2 plus and I'm converting it into cobalt 0. So I can write my own equation, cobalt 2 plus going into, going into cobalt 0. And so for this to be balanced, I need 2 electrons, and I need those 2 electrons on the left-hand side so that the charges are 0 overall on the left and 0 overall on the right? So my number of electrons is 2. I need 2 moles of electrons for every 1 mole of cobalt. And so I can use that as a conversion. So I'm going to take my 0.56 moles of electrons, and I'm going to do a ratio here that says that for every 2 moles of electrons, which is going to be on the bottom to cancel away, 2, oh my goodness, how much I hate doing this. 2 moles of electrons is going to be converted into 1 mole of cobalt. Cool. And from there, now we can go ahead and find the moles of cobalt, and that is 0.28 moles. And the last step is that I need to convert that into a mass. So I'm going to look at the periodic table and find the molar mass. And I'm going to say 0.28. Let's try that again. 0.28 moles of cobalt, and that's going to be multiplied by the molar mass. The molar mass of cobalt is 58.93 grams per mole, and that gives us a total of 16.8 grams of cobalt. That's that. That's it for that problem. And again, you could have done that whole thing in one single line and it would have probably been a little bit easier, but if you like it step by step, this is how you would do it. All right, the last part is on electroplating, which is basically where we utilize electrolysis in order to provide a coating onto a metal. Basically, to do that, what you do is that you have the 2 cells together in one solution. You're going to utilize the protective metal that you want to use as a coating as the anode, as here, for example, we're using silver as the anode. And then you're going to put the metal item that you want to protect or you want to cover at the cathode. The anode metal is going to oxidize to form ions that are then going to deposit onto the cathode. And so in this particular case, silver ions are going to come and are going to coat that fork. So let's go ahead and do a problem with electroplating. What we have is a chromium solution, chromium ion solution, which is electrolyzed and using 7.6 amps. What mass of chromium is plated after 2 days? All right, in this particular case, we're going to do it using dimensional analysis. All right, so we're going to start by converting the 2 days into hours. So 2 days, 1 day has 24 hours. Then from there, we know that 1 hour has 3,600 seconds. And that gives us a total of 172,800 seconds. That's 172,800. All right, from there, we're now going to set this up as one whole row. So I'm going to start with my amps, which is 7.6 coulombs per second. And I'm going to go ahead and multiply that by the time, which is 172,800 seconds. That right there, that whole thing is our current. Then I'm going to convert that current into moles of electrons by utilizing Faraday's constant. And in this case, Faraday's constant is going to be on the bottom as 96,485 coulombs per mole of electrons. From there, the next thing is to convert the moles of electrons into moles of chromium. And to do that, we have to think about how many electrons need to be transferred in order to go from chromium 3 plus into chromium 0. Well, to do that, I need 3 electrons to balance that equation out, right? So my number of electrons here is going to be that for every 3 moles, let's see, for every 3 moles of electrons, we're going to be forming 1 mole of chromium. The last step is to convert the moles of chromium into grams of chromium. And to do that, we're going to be utilizing the molar mass. Specifically, 1 mole of chromium weighs 51.996 grams of chromium. Once you multiply all of that out, you should get that your answer is about 235 grams. The end. So guys, that is the last calculation for General Chemistry 2 lectures. And the next 3 slides are actually just for your information if you would like to read them. It's about fuel cells and hydrogen fuel cells and more hydrogen fuel cells, which I think is a really exciting topic showing you the application of these concepts. All right, great. Have a great day, guys. Bye-bye.